my topic was dynamic monitoring of construction progress based on BIM. And the main challenge I'm trying to solve is like traditional construction progress monitoring is depend on the human. Like if you, for example, if the constructor want to report to the supervisor or construction company the progress of the construction, then the supervision or the construction management company has to send their personnel to the construction site. But this progress is time-consuming, labor-intensive, and inclined to errors. So the paper I was doing was trying to address those challenges by integrate information from point cloud and from the Revit model to to integrate this model and the point cloud to update the model automatically. So for example, here I have the Revit model and I have the point cloud of the building, and I put them together in the script I created so I can get the progress of each element. That's my goal of my thesis. Okay. So the first idea I thought was to compare the point cloud. This one is the as built point cloud with the as design point cloud to match each cloud together and see the progress of the elements. But this method takes so much time because it has so many calculations. For example, this point cloud has around 10 million points, needs 100 trillion times of calculation. So it is very hard for the average computer to handle this much of calculation. So this method could only used on the element analysis instead of the building or the projects. Okay, but based on this method I mentioned before, I create the method one in my thesis. This method one is to match as built and as design point cloud with the as built model, as design model. Sorry. So each point in the point cloud has a distance from all elements of the model. The method is to identify which element has the smallest distance. And if the minimum distance is smaller than the tolerance I defined in the script, that points is identified to be completed. To be if so at the end of the progress, I will have a list of the number of points for the as design points data and as built data. The number of as design data A is how many points should be on the elements, and as built data B, go here, is the number of points that are actually on the elements. Divide by B by A, which can give us the finished percentage of the element. This method greatly reduces the number of calculation. For example, a point cloud of 100 million points, the same example I mentioned before, needs around 10 billion times of calculation instead of 100 trillion times of calculation. This means it is 10,000 times faster than the method I mentioned before. Okay, so based on this methodology, I made a script using Grasshopper that can match point cloud and model automatically and update the model and or export to result to Excel. This screenshot is the Grasshopper I made, and this is the Excel sheet. Over here, you can see the progress, element ID, progress, and the update time. And this one is the case study I did on the Milan City Life. This is the residence building of Milano City Life, and this is the point cloud I made on this building. So you can see this point cloud is this part of the building, and I put this model and the point together, and it can integrate all the information from the scan to the model and update the model automatically. So if I click on the element of the Revit model, for example, over here, it can give me the progress of the elements. This wall is over here. I don't know if you can see it clearly, but this one is 27% finished. And using this method and this part of building, it takes around 10 to 15 minutes to get all the progress information from the point cloud. So it can be used in the real life already. And this one is the pipeline of my method one, which is to change the Revit model and to put into the Rhino and put into the Grasshopper and change from the point cloud to the cloud compare and manage the point cloud data and put in the Grasshopper also, and from the laser scanner to put into the Grasshopper and doing analysis in the Grasshopper script I created before. And after the analysis, it can update the model automatically or export to Excel sheet. And in the Excel sheet, we can choose to integrate with another source of information, for example, monthly or weekly report from the construction site. Then I created another script using Dynamo that can update the model automatically using the Excel sheet. Not going to talk about the detail of the progress, but you can see it in my thesis. Okay. Although I speed up the progress in the method one, but it still takes some time. For example, that part of building it takes 10 to 15 minutes. I think it's not good enough. It's not very fast. So I start to develop the method two. Method two is instead of matching the point to the model, I transfer the point cloud to the mesh and transfer the model to you can say it's point cloud to some kind of points, which is like I populate some points on the building elements, and the points on the element is defined by its volume. For example, if the volume of the element is smaller than zero point 0.1 cubic meter, I put 100 points on that element. Or if the volume of the element is bigger than 0 0.1 cubic meter, I put 200, etc. This method addresses the issue that the density of the point cloud is predefined by the machine. If it generates points evenly on the surface of the element, which we couldn't give the machine an order to identify which element is more element to put more points on it. So in some cases, for the small element, we don't have enough points on the element to be identified in the script. But using this method to even the smallest, for example, smaller than 0.1 cubic meter has at least 100 points. 100 points on the element, which gave us enough data to identify the elements and increase the accuracy of for the small elements. Okay. Each point on the model has a distance. So on distance to the mesh, the same as the method one. If the distance is smaller than the tolerance, the points can be identified as completed. And the total number of the points on the element B is defined by ourselves. So the progress of the elements are A divided by B, multiply 100%. Since the mesh generated from the points is identified as one object, so the points from the model are to match with one object instead of a lot of elements. The calculation is greatly reduced again. For example, using the same example as before, 10 million points. The point cloud with 10 million points with 1,000 building elements need around 300,000 times of calculation instead of 10 million times in method one and 3 trillion. I don't remember the first. Okay, the first one. Instead of 10 billion times in method one and 100 trillion times of calculation, which means 3,000 times faster. Okay, so I'm using the same case study, Milano City Life, and I put the point cloud and the model together to match them. And this time, this whole building, instead of this part of building, it takes only 10 to 20 seconds to integrate all the information from a point cloud to the model. So here you can see this whole building, and all the progress was updated. And this is a pipeline of the method tool. I transfer the Revit model to the Grasshopper from the Rhino into the Grasshopper, and the scan data from Cloud Compare and to the Grasshopper again, and update the model automatically or export to Excel and update the model using Dynamo script. And I made a comparison between method 1 and method 2. The advantage of method 2 are quite obvious because it's only part of this building. It takes 10 to 15 minutes, and this whole building for the method 2 only takes 10 to 15 seconds. So the method 2 are more powerful and faster and more accurate. But there are also some disadvantage for the method 2 because method 2 is to transfer the point cloud to the mesh first. So in this progress, we lose some information, for example, some details of point cloud, and also the RGB color of the point cloud is lost when I transfer the point cloud to the mesh. So there are some limits for the use of the method 2. But for the method 1, we can use almost all the scenarios. And since we have the progress of the element, the next step I want to do is to do the element analysis. Instead, when it comes to the element analysis, a very important thing about the element is to analyze the abnormal shape of the element. When analyze the abnormal shapes, three key points should be considered. First one is the volume, and second one is the section, and third one is the information integration. One thing worth notice that unlike the model element, the point cloud is not a consistent object. So when cutting through the points using a plan, it could not give us anything because the point cloud is not a consistent. So in order to get the sections of the point cloud, we need to project a small range of points on that plan to get a clear picture of the points cloud section. And based on these ideas, I create a script that can generate sections, volume, and integrate with Excel data automatically according to the requirements. And this screenshot is the Grasshopper script. And the case study I'm using is a ventilation shaft. This one is the ventilation shaft. This one the point cloud, and this one is the location of the shaft. There are 4 shafts altogether, and I'm using the shaft number 1. This shaft is around 500 meters long. Okay. Since after I put this point cloud into the script, Grasshopper script I made, I got this analysis result. You can see over here, I defined the tolerance of the distance, and all the distance beyond the tolerance, all the points was marked in the different color. So in this picture, you can see that you can see very clear that which part of the element is not very accurate, not what we expected actually. Okay, for example, also if I input, for example, the A3 part of the element, I input the number between this A3 area, for example, 943 and 929 into the Grasshopper script. It can give me automatically all the sections between this range. And this one is the example I did some examples, the sections of the point cloud. And also you can see there's some information about the sections, and this information is the result of integration of the Excel sheet. I talked to the people in the company. They want me to integrate these three columns into the sections. So in the script, I say put the column, for example, put column 7, column 10, and column 12 into the sections altogether. So it gave me all the data automatically. The conclusion is that to the use of the point cloud-based analysis in construction offer a rich array of application, allow for a better understanding of a complex project, and facilitating data-driven decision-making. The parametric programming greatly improve the speed and accuracy of the point cloud analysis, make the analysis of complex projects much easier. Thank you.